Hello, I welcome you all to this another interesting screencast, and the problem is determine the components of reaction at E. Right, so saying instead of just working on E, we are going to work on the reactions at E, A, okay, and let's also say B, C, and D. All right. So we have a frame here that is made out of four members, and then we have two force members. We have two force members. Okay, that is member AD and member CB or BC. Doesn't matter how you call it. So these are the two force members. And a two force member is a member that has only two forces at two locations. Two forces, no moments, two forces at two locations. And these forces are equal in magnitude, opposite in direction, and they are collinear. Alright. Two force member is a member that has two forces at two locations. No moments, only forces. These forces are equal in magnitude, they are opposite in direction, and they are collinear. All right. And the two force member can be of any shape. It can be like this, can be like this, can be a straight one. All right. Can be like this. Okay. So it doesn't matter. Okay. But it will have two forces at two locations, and these forces will be equal in magnitude and opposite in direction and collinear. Okay. No moments. Great. So we have these two members, and these members are member AD and member BC. Right. And we have a triangular distributed force on member AB. All right. So first things first, we are going to draw a free body diagram. Draw a free body diagram. And then once you've drawn a free body diagram, we are going to dismantle this particular frame. We'll start with AB, and then later on, yes, we'll dismantle it, then start work on AB, later on transfer the forces to the other members. Okay, great. So with this in mind, we know that to say member AD and BC are two force members. Okay, so we're going to have an equivalent force here, which is equal to just the area under the load diagram, and this is half times the length, which is 3, times the peak intensity, which is a 4. Okay, right? So we have half by 3 by 4. What does this give us? It gives us a 6, right? 6 kilonewtons, right? Half by 3 by 4 is a 6. Great. And since it's acting at the very midspan, because when you look at this loading, it's symmetrical. Okay, it's symmetrical about this axis. So expect the location to just be at the very center there. All right. So let's isolate a portion of that particular structure. Let's say we do this. Okay, and then to draw this quickly, isolate part of that and redraw it and then start working it out. So there we go, we have that load there like this. Okay, okay, so that is our A, and this is our B. The intensity there we said is 4 kilonewtons per meter, and we have our equivalent force, which is a 6 kilonewtons. Right, so at A, let's say we are going to have these reaction forces at A. We'll have the following forces. We'll have AY, okay, and then let's say we'll also have AX, like so. Then at B, let's say we'll have BY, which is equal to BC, because we have that two force member. Then here we have another member connected. Let's say this member is in tension. Let's say it is in tension, and let me just move this somewhere here like this. Let's say this is in tension, and this slope is as follows. We have a slope there of 1.5 rad. You can see this one, right? And then rise of 2, and therefore the hypotenuse is just 2 squared plus 1.5 squared root of 6.25. This becomes a 2.5 hypotenuse, and this is force AD, and it will have components. One component will be coming down like this, and this is AD by the rise divided by the hypotenuse, and then we'll have another one like this, which is AD by 1.5 divided by 2.5. All right, and then let's work out the length. We have a 1.5 meters there, and then we have the 1.5 meters there. Okay, and then we do have another member, which is this one. Okay, so this member here, this point is B and this point is C. So here we are going to have the following reaction forces. Okay, so this is equal to BC, and so is this one there. You can even call it C, no big deal. And then here we have another member, okay, and this member at this point, which is E, you expect reaction force of EY and another reaction force there of EX. And then since we had assumed ED to be in tension, we expect the same direction there. This is, AD is in tension. This is our AD, and the slope is the same, which is just a 1.5 by I2 by there a 2.5. And then we have a component there. We have a component, and then we have a component. This component there we said is AD by 2 divided by 2.5, And then we have another component here, which is just AD by 1.5 divided by 2.5. And then finally, HC, we do have an applied force of 5 kilonewtons, but we also have another one coming from the two force member, which is a BC. Okay, right, so we have this system and the length is the same. The length for this is the same. Let me just center this properly. It has the same dimensions like the one on top, so the same dimensions will work for both. So we are going to apply the equations of equilibrium on one above and at the bottom, then work it out, because this is one system interconnected using pins, and we cannot just work it directly just the way it is. We need to have it dismantled so that we can effectively apply the equations of equilibrium, and that's the reason we have done this. Alright, let's start. So we have summation of moments about point A equal to 0. Starting with this, so that we find BC. Once we have BC, we can find AD, we can find EY, EX, and the rest. Alright, so what do we have there? We have, that is about A. We have a minus moment 6 by 1.5 plus BC, which is BY by 3 equal to 0. Therefore, our BC is just going to be equal to minus 6 by 1.5 divided by 3. So this is equal to 3 kilonewtons. And for sure, BC is in compression. And then we have summation of forces in the Y equal to 0. We are still on member AB. Still on member AB. So here we are going to have minus AD by 2 divided by 2.5 plus AY minus 6 plus BC equal to 0. Okay, we've already calculated what BC is, so we can just replace it there. And once we do so, then we'll find that our AY is just going to be equal to what is our AY going to be equal to? So we have a minus 6 plus 3, which is a minus, so this becomes a 3 plus 2 divided by 2.5 plus 0.8 AD. Alright, so that is our AY. So let's find what AD is. So let's go to member ED. This one is D here. EDC, so that we apply the equations of equilibrium. Okay, like so. So we'll do that. So say summation of moments about point E equal to 0 and clockwise being our reference. What we have? We have 3 BC. We said this BC is equal to 3. So is this BC here? Alright. So 3 plus 5 is 8. So we have a negative moment 8 by 3. Okay, plus AD by 2 divided by 2.5 times the lever arm, which is 1.5 equal to 0. And then our AD is just going to be equal to Our AD is just equal to minus 8 by 3 divided by 2 by 1.5 divided by 2.5. Great. So we have AD equal to 20 kilonewtons. So minus 24 divided by 2 by 1.5 divided by 2.5, 20. All right. So AD is equal to 20. This is equal to 20. Great. So let's find what EY is. So summation of forces in the y direction equal to 0. We have EY plus AD 2 divided by 2.5 minus 8. We already have what AD is, we just replace it there. And once we do so, then we'll find that our EY is just equal to 20 by 2 divided by 2.5 is 16 minus 8, which is 8. Therefore, this gives us a negative 8 kilonewtons, just direction changes. Then summation of forces in the x direction equal to 0. What do we have? We have EX minus AD by 1.5 divided by 2.5 equal to 0. We've already found what AD rather is, so we just replace AD, we replace AD where we need to have it replaced there. And once we do so, our EX is just going to be equal to, so AD is 20 times 1.5 divided by 2.5. So this gives us a positive 12 kilonewtons. Then let's get back to AY. We had said AY is equal to 3 plus 0.8 AD. And we found that our AD is just equal to 20 kilonewtons. So replacing this here, right, we'll find that our AY is just equal to 3 plus 0.8 by 20. This gives us a 19 kilonewtons, right? A 19 kilonewtons. Is that fine? So let's say where is our summation of forces? So we have minus 20 by 2 over 2.5 plus 19 minus 6 plus 3, then we have a 0. Great. So that is fine. That is our AY. And then summation of forces in the x direction. Summation of forces in the x direction. We want to find AX. So we have AX plus AD by 1.5 divided by 2.5 equal to 0. So we have we replace that AD there, we'll find that our AX is just equal to 20 by 1.5 divided by 2.5. This gives us a minus 12, which just indicates change of direction. So AX, the direction changes to be facing this side, and this is a 12. AY, what is AY? AY is here, and let's look at the direction. The direction for AY maintains. The direction for AY maintains and is equal to 19. Okay. And then EY direction changes. EY direction changes is going to be facing downwards and is equal to 8. EX direction is okay and is equal to 12. Okay, what else? I think this is about it. Let's just outline the final answers. We have BC, which is in compression for the two force member, and then we have AD, which is in tension. Then we have EY, just the direction that changes. Then we have EX, the direction is the same. Then we have EY, and the direction is the same. We have AX, the direction changes. I think this is about it. This is really about it. We have found all the reaction forces, right? 1, 2, 3, 4, 5, 6. Right, 1, 2, 3, 4, 5, 6. Great. So I hope the video was helpful. This is BC, which is 3. This is BC, which is 3. I hope the video was helpful. If it was, give me a thumbs up, like my video, and continue subscribing and liking my channel. Bye bye, and see you in my next screencast.